Today, I'm going to be talking about the LP spread and restricted isometry properties of sparse random matrices. I'm Peter, and this is joint work with Venkat Guruswamy at UC Berkeley and Jonathan Moshev at Ben-Gurion University. So I'd like to start off the talk by just talking about this really cool fact. So let's let n be a large integer, and let's let m be a small constant times n, say like 1 over 100. And we're going to let A be a random m by n matrix with independent plus or minus 1 entries. So A will look something like this. It'll be a rectangular matrix. And we'll let X be the kernel of A, which will be a subspace of Rn of dimension least n minus m, because it's specified by m linear constraints. And in particular, the subspace will have dimension like 0.99 times n. And this subspace X with high probability will have the following cool property. That is that X will be a good Euclidean section of L1. And this means that the maximum over any vector X that's non-zero in the subspace of the L1, L2 distortion of X is at most a constant, where the L1, L2 distortion is simply the ratio of the L2 norm to the L1 norm up to the scaling factor of square root n. And if you haven't seen this property before, it might seem a little bit opaque, so let me just explain in more detail what it means and why this is a very cool property. So we recall that the L1 norm of any vector X is always at least its L2 norm and is, by the Cauchy-Schwarz inequality, at most square root n times the L2 norm. And this upper bound is tight when X is the all ones vector, or all the coordinates of X are equal. That is when X is dense, or the L2 mass of X is kind of evenly spread out among the coordinates of X. And this lower bound is tight when X is a unit coordinate vector. That is when X is sparse, or the L2 mass of X is kind of concentrated on a small number of its coordinates. And when we kind of return to distortion here, this says that the distortion of X will be like square root n when X is sparse, and will be constant when X is dense. And yeah, I guess the distortion is always between 1 and square root n, also by this inequality. And so this in particular implies that when X is a good Euclidean section of L1, it means that X does not contain any sparse vectors that are like vectors that are sparse in this analytic L1, L2 distorted sense. In particular, all vectors in the subspace have very good L1, L2 distortion. In particular, it's a constant. And because of this connection between sparsity and this L1, L2 distortion, we can actually rephrase being a good Euclidean section in the following equivalent way. We can equivalently say that X is an L2 spread subspace. And this means that every non-zero vector in the subspace X is L2 incompressible. That is, it's far in L2 distance from all sparse vectors. More formally, for any delta n sparse vector Y, the L2 distance between X and Y will be at least epsilon times the L2 norm of X, where delta and epsilon are constants. They'll in fact depend on this ratio of m to n, which here I've set to be like 1 over 100. But regardless, when m over n is a constant, the delta and epsilon will be constants. So that's what it means for a subspace to be L2 spread. And this should remind you maybe of the definition of an error correcting code, where for an error correcting code, we say like if we take a random m by n matrix of F2 and we let Y be the kernel of B, then Y is a good error correcting code, meaning that it does not contain any delta n sparse vector. And so not only does X being L2 spread mean that X does not contain any delta m sparse vector, it does not even contain a vector that is close to being sparse. So in this sense, we can think of spread subspaces as being like real analogs of error correcting codes. And just like error correcting codes, one big goal in Euclidean sections is to get an explicit construction of L2 spread subspaces of high dimension. Or at the very least, if we cannot give an explicit construction, we would like to get a kind of partial de-randomization and generate a subspace X using as little randomness as possible. And so along these lines of work, there is this theorem due to Guruswamy-Lee-Razborov, which shows explicit X, which gets distortion that's log n to the log n. And this is the best known explicit subspace. Although I should mention this other work due to Piotr Indyk that achieves constant distortion, but dimension that is slightly sublinear in n. And so for the purposes of the talk, I'm only going to be considering subspaces X, which have dimensions, say like at least 0.99 n or something very high and linear in n. So this construction won't really count. as far as partial de-randomizations go, there's this theorem due to Guruswamy, Lee, and Victorson that show that using n to the delta randomness, we can actually construct a subspace X that has distortion that's exponential in 1 over delta. And the later work of Indyk and Zark got the same guarantee, but using a different construction X. And so one cool, interesting thing about all these constructions is that they're coming from analogs of constructions of error-correcting codes. And so this is really cementing this kind of intuition on the previous slide that like an L2 spread subspace is somewhat similar to an error correcting code. It's like a real analog of an error correcting code. And like one way to kind of think of this, make this more concrete, is to just observe that these constructions really are coming from constructions of error correcting codes. So the GLR work is coming from a Tanner code-like construction. The GLW construction is using essentially Sipser-Spielman expander codes, and the Indyk-Zark construction is using tensor product codes. And one interesting property that all these works have is that in all of the above constructions, the subspace X can be written as the kernel of a sparse matrix. And this sparsity property is just inherited from the underlying error-correcting codes because Tanner codes, Sipser-Spielman expander codes, and tensor product codes can all be written as the kernel of sparse matrices. Right, so they're kind of the sparsity is really being inherited from the construction of error-correcting codes. And in light of this connection, the work of GLW asks the following question, which is there a constant sparse matrix which achieves distortion that's constant? The distortion of kernel A will be a constant. And by constant sparsity, simply mean that every row and every column in A has at most a constant number of non-zero entries. And the work of GLW and IS both show that we can achieve distortion n to the 1 over log S when the matrix A has sparsity S. And this is pretty bad because if the sparsity S is constant, then this will be distortion n to some constant. Remember, the worst distortion you can have is square root n. And so up to a constant factor in the exponent, this will be kind of maximally bad distortion. Okay. So one way we can try to answer this question of GLW is we can try what happens and like to try to analyze what happens when A is a random sparse matrix. And so that's what we're going to do in our work. And we're going to consider the following random matrix model. And it's a pretty natural model. We'll call a matrix A with entries that are all going to be either 0, 1, or -1. We're going to call it ST biregular if every row has exactly S non-zero entries and every column has exactly T non-zero entries. And we'll let this parameter alpha be the ratio of M over N. And by a double counting argument, we can see that this is also going to be T over S. And this matrix A will look something like this. Okay, as you can see here, I've made every row of A have 3 non-zero entries and every column have 2 non-zero entries. And so this is a biregular matrix. And our random matrix model will be that we'll simply sample a uniformly random ST biregular matrix, and alpha will be some fixed constant. And for simplicity in this talk, I'll also just hard code alpha to be 1 over 100, and I'll assume that S is always at most a constant. Okay, and this model is in fact equivalent to the following thing where we set A to be the signed adjacency matrix of a random TS biregular bipartite graph, where the left vertices are N and the right vertices are M. And the non-zero entries of A are simply specifying where the edges are, and then the signs are chosen uniformly at random. So for example, here in the matrix A, we can see that the right vertices correspond to rows of the matrix A, and we can see that the first right vertex is connected to vertices 1, 3, and 6 on the left. And as you can see on this bipartite graph here, I have made the first right vertex be connected to vertices 1, 3, and 6 as well. So this is kind of the equivalence between these matrices A and bipartite graphs. Cool. So we're going to let A be a uniformly random ST biregular matrix where alpha is this constant. And we can observe that the kernel of A is a real analog of a random low density parity check code. And a low LDPC code is simply a code that's specified as the kernel of a sparse matrix. And that's essentially what we're doing here. And for those of you that know, LDPC code is actually a really good code. Like a random LDPC code achieves also like the almost GV bound. It's like almost as good as a random code. And so if we just put this table here, we know that kernel of A for error correcting codes is essentially as good as random. And for Euclidean sections, that's what we're going to try to study. And so by analogy, this analogy from error correcting codes in L2 spread subspaces or Euclidean sections, we might expect the kernel of A to have constant distortion, right? Like if their analogy is going to hold, like this should happen. It should be almost as good as like a random matrix A. But in fact, we show that this is not the case, somewhat surprisingly. So this is our first theorem. We show that if A is a random sparse matrix, then with high probability, the distortion of the kernel of A will be like n to the 1 over log S, and up to a constant factor, the exponent, this is also tight. And in particular, when S is a constant, this is like n to the order 1, and that's almost maximally bad because, as I said earlier, the worst case distortion you can have is square root n. So kernel of A for Euclidean sections, we can now fill in this table. It's almost maximally bad. And another thing to point out is there's this 1 over log S dependence in the exponent, and this is really popping up both in the works of GLW and Nick Zarek, and now in our work as well. So this is really giving some indication that this kind of sparsity versus distortion trade-off is somewhat necessary, even though we haven't like fully proven it. The fact that it holds for the 2 prior works and as well as our work is kind of giving some evidence that this is perhaps the case. Okay, so now I would like to give a proof sketch, at least of the lower bound on the distortion of kernel of A in our theorem. So I'm going to let A be this uniformly random ST biregular matrix. And what we need to do is we need to show that there is an X in the kernel of A that is close to a sparse vector. So let's pretend for now that the matrix A is unsigned. And our first step in the proof is we're going to find a sparse vector Y, where when we look at A times Y and take the L2 norm, it's going to be a very small L2 norm, but Y itself will have large L2 norm, like a constant. And the intuition here is that such a vector should intuitively feel close to being in the kernel of A, because if Y was exactly in the kernel, for example, AY would be 0. So when AY is small, it should intuitively feel like Y is close to being in the kernel. And what we're going to do is we're going to exploit this connection between A and bipartite graph G. And because A is random, the bipartite graph G will be a good expander because it's a random graph as well. And in particular, we'll obtain a tree of very large depth, like log n depth. And so we can just find this tree and we can write out the tree, and the tree will like have alternating levels of left and right vertices. And this Y, this vector Y will have non-zero entries corresponding to the blue vertices, that is the left vertices on the tree. And we'll set Y sub V to be 0 for all left vertices V that are not in the tree. And just by construction, because the tree has log n depth, if we set the constant in the log n to not be too large, the number of vertices in the tree as the number of left vertices will be little o of n, so the vector Y will be sparse. Okay, so we now need to explain how to construct the vector Y. And oh, I guess I forgot to mention that the degree of any left vertex in the tree is T, because that's this regularity property, and the degree of any right vertex is S minus 1, or sorry, it's S, but in particular, it only has S minus 1 children. Okay, now the L2 norm squared of AY is simply, what we do is we sum over all right vertices, which correspond to the rows of A, and then we sum over all the blue vertices, accumulate the sum over Y sub V over all the blue vertices neighboring Y, or neighboring the red vertex, and then we square it. And that gives us the L2 mass squared of AY. So we now need to construct this vector Y, and we'll do it as follows. We'll first just set the root to have Y sub V equal to 1, and then we'll set the next layer of the tree. We'll pick Y sub V such that when we sum over the red vertex, all the mass will cancel. So, and we'll do this in a way so like we'll evenly spread out the mass. So that is, we'll set Y sub V to be like minus 1 over S minus 1, which in particular means that when we sum over a right vertex in the middle, we'll get S minus 1 times minus 1 over S minus 1, which is minus 1, and then plus the 1 coming from the root, so it sums to 0. And we've kind of evenly spread out this mass across all the children of the right vertex. So that's just the construction. And we can just repeat this for every level of the tree. So say in the third level of the tree, we'll have Y sub V being 1 over S minus 1 squared. in the fifth level, or sorry, in the fourth level of left vertices, it'll be like 1 over s minus 1 cubed, etc. And as you can see from the construction, we're just making it so if we look at any right vertex on the interior of the tree, when we sum over its neighbors, all the mass will cancel. And so all we'll be left with is the sum over the leaves of the mass at the leaf squared. And the mass at the leaf will just be 1 over s to the depth, and then we square it, so it's 1 over s to the 2d. And a simple calculation shows that there's t times st to the d leaves. And now we can compute, and we see that this s to the d in the numerator cancels with one of the s to the d's in the denominator, and we get t times t over s to the d. T over s, you may recall, was alpha. Alpha is a small constant, d is log n, so this is little o of 1. And that's what we're trying to show. And I guess I already kind of argued that the vector y was sparse because the tree contains a sublinear fraction of the vertices in the full bipartite graph. So the only thing now to show is that the L2 norm of y is at least a constant, but this is obvious because this vector, this y sub v on the root is 1. So in particular, the L2 norm of y has to be at least 1. So that's step 1 of the proof. In step 2, we now need to round y to a vector x in kernel of A and then argue that y and x are close. And how are we going to do this? Well, we're just going to project y onto the kernel of A. And this essentially gives the closest x in L2 distance by construction. But we do need to analyze how far or how close x is to y. And the intuition I mentioned earlier is that because AY has small L2 norm, this intuitively feels like y should be close to the kernel of A. But formally, this is not quite true, because it could be that y is a right singular vector of the matrix A with singular value little o of 1. And then y is orthogonal to the kernel. So when we project, we would get the all zeros vector. And in particular, x and y would be very far. So formally, we can control this distance by looking at the L2 norm of AY divided by the minimum singular value of A. And this means that the last step of the proof is we need to show that the minimum singular value of A is at least some constant. And so that's our second theorem. We get a very sharp bound on singular values of randomly signed adjacency matrices of ST biregular random bipartite graphs. We show that all singular values must be between like square root s plus or minus square root t. And in particular, the minimum singular value will be at least a constant. And the sharp bound on the minimum singular value is actually needed in order to handle the case when alpha is a constant that's kind of close to 1. We could, if we let alpha be a sufficiently small constant, we could have gotten away with, say, using off-the-shelf matrix concentration bounds, but we need the sharper statement that we prove in order to handle constant alpha, like all constant alpha. And the proof of this theorem is just using the Harabas formula, non-backtracking matrices, and all these now they're complicated techniques, but now somewhat standard techniques to analyze singular values or eigenvalues of sparse random matrices. Okay, so that's like all I really want to say about L2 spread. We now know that the L2 spread of the kernel of A is quite poor. We kind of have a complete characterization of it. But you might have asked, why are we looking at the L2 norm? Why don't we consider, say, the LP norm? So that's what we're going to now look at. We recall this definition of L2 spread, and we can easily generalize it to LP spread, where we just replace essentially the L2 norm with the LP norm everywhere. We want, for example, every vector x to be far and now an LP distance from all sparse vectors. And we also get an analogous definition of the distortion, where the distortion is the ratio of the LP to the L1 norm rather than the L2 to the L1 norm. And the scaling factor is now this n to the 1 minus 1 over p, which is like the equivalent Holder factor for general p. Okay, a thing to point out is that we can only achieve dimension that's linear at n when p is less than or equal to 2 for the remainder. So for the remainder of the talk, we'll let p be at most 2. And this LP spread property is in fact stronger when p increases. So if x is LP spread, then it's also LQ spread for any q less than or equal to p. The thing is, when we look at LP spread subspaces, we actually know of explicit constructions. So there's this theorem due to Karnin, which gets an explicit construction of a subspace X, where the distortion is constant for, and you can get an explicit construction for any p less than 2. And as you might guess by now, the subspace X can be written as the kernel of a sparse matrix A. Okay, so there's not really much to do here in terms of explicit constructions. So we're actually going to look at a different property, which is the LP restricted isometry property. It's closely related to the property of LP spread, and it's actually a very important property in the field of compressed sensing. So we're going to say that a matrix is LP RIP if for any delta n sparse vector y, when we look at AY, look at its LP norm, it's within like a 1 plus or minus epsilon of the LP norm of y. And it's simple to, like a very simple computation shows that if A is LP RIP, then its kernel is LP spread. And it's also easy to show that a kernel being LP spread is equivalent to this distortion being constant. But the converse here is not true. So just if the kernel of A is LP spread, it does not imply that A is LP RIP. So LP RIP is a strictly stronger property than being LP spread. And so there's this theorem of Karnin that I already mentioned, which gets constant distortion. The matrix A is sparse, but as you might guess by now, it's not LP RIP. And the only explicit construction of an LP RIP matrix that we know of is this theorem due to Berinde, Gilbert, Inde, Karloff, and Strauss, which gives an explicit construction of an L1 RIP matrix, where again, this matrix A will be sparse. And in fact, it's very simple construction. The matrix A will just be any unsigned even adjacency matrix of a bipartite expander. Okay, so that's LP RIP. And in fact, in our third theorem, we extend that previous result where we show that any adjacency matrix of a bipartite expander will be LP RIP, provided that this the sparsity or like the degree of the bipartite expander is above some threshold. That's a constant, but the constant depends on P. And we also show that if it's below a different threshold, the constant's different here in the second threshold, then it's not LP RIP. And we get a couple corollaries from this. The first is that if we take a random bipartite graph, since it's a good expander, we show that a random sparse matrix will also be LP RIP. And when we plug in explicit constructions of expanders, we get an explicit construction of an LP RIP matrix. And one thing to point out here, though, is that theorems 3 and corollary 4 are able to achieve LP RIP for any p, constant p less than 2, whereas our corollary 5 is only able to get up to some threshold p naught, where p naught is strictly greater than 1, but also less than 2. So I'll explain what's going on here in a moment, but this is something to point out. So because LP spread and LP RIP are kind of similar properties, and our corollary is similar to this prior work of Karnin, I just want to take a moment and compare the two results. So the difference here is in our corollary 5, we managed to prove LP RIP, whereas Karnin only achieves LP spread, which is a strictly weaker property. On the other hand, our corollary 5 only gets LP RIP up to some constant threshold P naught, whereas Karnin achieves all P less than 2. So in some sense, our corollary is incomparable to this work, to the work of Karnin, because we're stronger in one sense, but weaker in the other. Another interesting thing is our construction is actually very simple. We just take the adjacency matrix of a bipartite expander. In some sense, I kind of feel like this is almost like the simplest possible construction imaginable. On the other hand, it's not really much of an advantage over the work of Karnin because Karnin's construction isn't too complicated either. So now let's just take a moment. I'll explain why we have this threshold P naught. It comes from the fact that we need like a very strong expansion property from the bipartite expanders. That is, we need all sets S of the left vertices to have at least T times 1 minus epsilon times S right neighbors. Now remember, T is the left degree, so the expansion error is this epsilon. And we need epsilon to actually be 1 over T, like order 1 over the left degree, which is a very stringent, very strong expansion. And this is actually achieved by random graphs, but the CRVW expanders that we use only achieve epsilon that's order 1 over T to some tau, where tau is a constant, but it's less than 1. And this in particular means that our P naught threshold only becomes 1 plus tau, whereas if we had a random graph, we can achieve tau equals 1 and then get the threshold P naught equals 2. So that's kind of what's going on here. And the reason Karnin is able to handle all P less than 2 is his construction is using a weaker expansion property for which explicit constructions are met. So just to summarize, our theorem 1, we show the kernel of a random sparse matrix is not L2 spread. And we prove this using our second theorem, where we show very sharp singular value bounds on signed bipartite graphs. And in our third theorem, we show that the adjacency matrix of a bipartite expander is actually LP-RIP. And then as a corollary, we get the kernel of a random sparse matrix is also LP spread for P less than 2. And also a random sparse matrix is even LP-RIP. And then as a corollary 5, we get an explicit construction of an LP-RIP matrix. And unfortunately, we don't get all the way up to all P less than 2, but we get the sum P naught, where P naught is a constant greater than 1. So in particular, we've generalized the previous result that only worked for like P equals 1. And that's all I have time to say. Thanks for listening. Hope you enjoyed the talk.